magnetic braking with Faraday's law. So to begin, the purpose of this lab was to create a computational model demonstrating the magnetic braking effect observed when a magnet is dropped through a metal tube, the metal in this case being copper. This lab marked a culmination of many physics principles from Physics 1 and Physics 2. I applied principles of magnetism, including magnetic field and magnetic force, Faraday's law, Lenz's law, Ohm's law, which is not mentioned here, and then Newton's second law, which is we learned in Physics 1. So for the procedure of this experiment, we dropped a magnet through a copper tube. To observe the magnetic braking phenomenon, we dropped the magnet through the tube held vertically and recorded the time for the magnet to reach the bottom of the tube. This drop was repeated 3 times to obtain 3 different time values for this drop. Properties of the magnet include the magnet weighing 23 grams, the mu of the magnet, or the magnetic dipole moment, was 2.959 amperes times meters squared, and this was calculated in lab 4, last lab. And the properties of the copper tube include the resistivity, which was found online. It's 1.68 times 10 to the minus 8 ohms. The length of the tube was 100.5 centimeters, width of the tube was 1.5 centimeters, and the inner radius of the tube was 1.3 centimeters. So the results of this experiment, average drop time of 13.15 seconds for 3 trials. Then here's a look at the glow script code. This slide details the setup and initial conditions. So the initial velocity of the bar magnet was just 0 in the x, y, and z components, and time starts at 0. Physical constants in this experiment are the Km mu naught over 4 pi, which is 1 times 10 to the minus 7th, the resistivity of copper, 1.68 times 10 to the minus 8, and the gravitational constant, 9.81. And the properties of the magnet, mass, and magnetic dipole moment are both represented here. And then last piece of code demonstrates the visualization of the bar magnet, the position, bar magnitude, and then the direction of the bar magnet, the mu hat. And here we begin calculating first the magnetic field of the bar magnet and the magnetic flux, which are arguably the 2 most important components of this lab. The function for calculating magnetic field is the same function used in lab 4, previous lab. And then we created a new function in this lab calculating magnetic flux, d flux dt, which ends up being added all together to get the total flux. Then calculated magnetic force on the ring, which, as I had hinted before, we end up adding all of the d flux dt values to get a total magnetic force on the magnet, which we then add to the gravitational force to get the total net force on the magnet. And we use this net force to update the bar magnet's velocity and its position. And this is a practice that we did in almost all the Physics 1 lab. So it's a good tying all of our new knowledge together into one final lab. Then this is a look at the glow script model results. So the velocity is initially, increasing rapidly until the bar magnet reaches the tube almost right away. And then the velocity remains consistent at negative 0.15 meters per second until it drops and speeds up again after it leaves the copper tube. And then the copper tube is visualized to the right, and the time the model predicted for the magnet to fall was 6.662 seconds. So to compare, the experimental results showed the magnet to fall, to take 13.15 seconds to fall through the tube, whereas the model results predicted the magnet to fall in about half the time, in 6.662 seconds. So some assumptions made in this experiment were that the bar magnet acted as a dipole, that air resistance was negligible, and that only forces acting on the magnet are gravity and the magnetic force. So just 2 forces, no drag or anything else. Some potential errors. Small thing, potential slight inconsistencies in the stopwatch recordings because it was manually recorded, not through like a high-tech camera or anything. So a little bit of lack of precision there. But then the big thing is that the dipole moment was actually stronger, could have actually been stronger than the value calculated in lab 4. A weaker dipole moment would produce the results seen in the model. a magnet falling faster through the copper tube because it experiences less magnetic force of attraction to the copper tube due to a weaker dipole moment. Some discussion questions. What if the resistivity of the conductor were reduced to as close as possible to zero? The magnet would fall more slowly because decreasing resistivity facilitates electron movement that contributes to current and allows magnetic force to be stronger. This relationship is given in Ohm's law, where the voltage is equal to current times resistance. What if holes were cut into the tube? How would this affect the ring currents? Holes in the tube would decrease the number of current rings, decreasing the overall surface area of area for the current to travel, so the magnet would experience less magnetic attractive force and would fall through the copper tube more quickly. And that's all. Thank you.